Hello and welcome to our third webinar in the Research Clues to Appreciating a New Era of Cannabinoid Conundrums webinar series. Today's webinar will be presented by Dr. Walter Brent Wilson, a research chemist with NIST. Without further delay, here is Dr. Wilson.
Hello everyone, and thank you for taking the time to attend today's webinar, where I'll be focusing on the development of analytical methods for measuring delta-9 THC in cannabis products. The work here at NIST started because of the passage of the 2018 U.S. Farm Bill that legalized hemp by removing it from the Schedule I controlled substance list. At the same time, it provided a definition that basically stated that hemp was a material, cannabis plant material that had a delta-9 THC concentration of not more than 0.3% on a dry weight basis. And any type of cannabis plant which was higher than 0.3%, which is generally called marijuana, it was still deemed to be on the Schedule I controlled substance list. And this really opened up a really quantitative need in the forensic space for being able to distinguish between hemp and marijuana in our laboratories. So the primary focus of Analyte is delta-9 THC based on the ruling in the Farm Bill. However, the USDA came out with a final ruling that stated samples must be tested using a post-decarboxylation method or similar reliable analytical method, where it takes into account the total delta-9 THC concentration reported in the sample. So this takes into account the conversion of THCA into delta-9 THC. So basically, THC is the acidic compound that's predominantly found in hemp samples that under heated conditions will convert into delta-9 THC. And there's an equation here that shows you how you can calculate the total potential delta-9 THC a sample may have. So in addition to delta-9 THC and THCA, forensic labs have a lot of interest in CBD and CBDA as they are predominant analytes found in cannabis products, plant or finished products. However, more recently, there's been an explosion essentially of delta-8 THC products and delta-9 THC products. These are two isomers of delta-9 that are of belief to have some psychoactive effect in the plant material. However, these two isomers do not generally exist at very high concentrations in plant. However, scientists have figured out a way to convert from CBD into delta-8. That's why you see so many delta-8 products on the marketplace. So in general, I'm going to talk about a lot of the work we've been doing at NIST for analytical methods. We do have a website. If you Google NIST cannabis, it'll be the first thing that probably comes up. There's for NIST tools for cannabis laboratory quality assurance. Highlights a lot of the different presentations we give, publications, but also like training videos that we do that we develop specifically for the cannabis and forensic science industries. So just a big picture overview of our cannabis research program first. Here in the Chemical Sciences Division, we centered around the four main analytes initially for the delta-9 THC, THCA, CBD, and CBDA. With this, we have been focusing on developing cannabis reference material. The first hemp plant reference material is projected to be out this year. That will take into account, will have values assigned to it for THCA, total THC, delta-9 THC, CBD, CBDA. Went through the rigorous process just like we've done for any of our other materials that NIST is very well known for. And it will come with a type of certificate similar to any other material that we have. In conjunction with that, we've also been working on what's called a Cannabis Laboratory Quality Assurance Program, short CANQAP. This is a interlaboratory studies program almost identical to proficiency testing, except we do not provide you with a pass, fail, and grade, but you get homogenized plant materials that were prepared either by NIST or obtained by leaders in the industry to be able to evaluate your capabilities, but also compare it to other people in the industry and as well compare it to NIST. So as part of this, both of these types of materials that we develop here at NIST go through the same type of process, where it starts with some type of samples being received, either through purchasing of hemp plant biomass material or obtaining adjudicated samples from a local forensic laboratory. These materials are ground, sieved, and mixed to ensure the homogeneity across the entire lot, packaged, and before any samples are shipped out from NIST, because we have to ensure that we're shipping hemp samples that are below the 0.3% threshold, we have to do sample analysis on them, which involves some type of extraction process. And then generally we use LC-PDA for the screening of these samples. But we do have, in general, three primary methods we've developed here at NIST, the LC-PDA method, the LC tandem mass spec, and a GCMS. All of these are the analytical techniques, but a thorough study has been done on developing extraction methods for the analysis prior, or for the extraction prior to analysis of these methods. Now, a lot of the work we have done so far is centered around what you would typically find in normal hemp or marijuana samples out that were grown here in the U.S. So we have started, we are in the process of expanding out. And I'll have some research on it at the end where we looked at different types of samples like vapes and oils. We've got an ongoing project looking at gummies, but also looking at Delta 8 THC and Delta 10 THC products, specifically analytes in these products, but also including exo-THC, which has become very popular as a degradation product in a lot of these finished products. So first, just a general overview of what's possible for being used for quantitative methods. Generally can be separated out based on chromatographic and spectroscopic methods. LC and GC are the two primary methods used in the forensic space. LC can be combined with UV detector or a single quad mass spectrometer. GC can be used with a mass spec or an FID, and then both can also incorporate a tandem mass spectrometry in their flow. Now, in general, LC mass spec and GC mass spec are considered the gold standards in forensics for drug analysis. NIST has developed methods centering around LC-UV and GC, primarily what we use here, but also the tandem mass spec, as I mentioned on the previous slide. We have done a lot of work with infrared spectroscopy using benchtop instruments, but also potentially portable instruments. I'm not going to have the time to go into that here today, but we are in the process of submitting a paper on a lot of the characterization work that we did over 4 different types of portable IR devices and benchtop instrumentation. So please look forward to that if you are interested in that information. So the GCMS method here is summarized that we use here at NIST. We chose the DB35MS column over the typical DB5. The more polarity of the stationary phase allow for a much better separation, which is shown here at the top right of the screen, where you can easily baseline separate almost completely 9 cannabinoids from each other, mainly focusing on the Delta 9 THC, where Delta 8 is clearly separated out from it. But the other aspect of what we did in our GCMS work was we centered around trying to develop what's called a selective ion monitoring method. So where instead of a forensic lab having to collect a full scan of it, where you're going to decrease your sensitivity of your analytical method, you could do a SIM mode, where in this case, we basically choose the mass spectral peak shown here in the slide. It's 299, and then we have 3 other peaks showing up that are used as qualifier ions for the identification of THC in your run. So essentially what you're able to do is get a much improved limits of detection or limits of quantitation, while also still getting the confirmation from your mass spectra. And as a result, we also are able to use a deuterated labeled Delta 9 THC isomer or analyte as an internal standard that uses a 302 master charge. So we're incorporating an internal standard, but also minimizing the number of ions we're looking for in the GC run. And there at the bottom, just an example of what one of the runs looks like for a high sample of CBD. So the primary issue with GC for quantitative analysis deals with the decarboxylation of THCA into THC. When you inject a sample in inlet, any of the acidic form is going to be converted to Delta 9 THC. However, it's not 100% conversion. The papers report, here's an example from Dusty, 2005, where it ranges from above 45% to a little above 65% for the conversion rate. So it's not 100%. So at some point in the process, you are losing some of your THCA and it's not being converted over to delta-9 THC. So as a result from that, a lot of forensic laboratories have been centering around using what some call a semi-quantitative method or just a threshold endpoint comparison. This is where they take and they extract the delta-9 THC from the plant sample, spike it with a known amount of an internal standard at roughly a ratio at 1% for the internal standard. And if the peak for delta-9 THC is greater than that, it's considered marijuana. If it's lower than that, it's considered hemp. They're doing 1% to really account for the variation you could see from the sample to sample, but also a lot of it's pretty difficult to make hemp that's below the 0.3%. And a lot of samples I'm going to show you later on, you're going to see a lot that fall between the 0.3 and 1% range. So the primary method we use here for screening a lot of samples is LC-PDA. We use the cannabis analyzer from Sumatsu. It's the same as any LC-PDA system that you could buy from another manufacturer. This one particularly was built as an all-in-one system targeting 2 forensic laboratories for cannabis analysis. It provides you with 3D chromatograms that allow you to collect 2D chromatograms as shown here on the top right, but also using the absorbance spectra to confirm the identity potentially of the analyte that you're looking at. Similar to mass spec, but it's not considered as confident of a distinguisher identification purposes as the mass spec. For our method, we look at 11 cannabinoids at single wavelength 220 nanometers for quantitative purposes. And here on the right, I'm showing an example of what the calibration curve generally looks like. We targeted a very narrow range. One of the things I can tell you that does happen a lot, why people get results that are varying off, is that they try to use a 3 to 4 calibration range for their analysis. We've seen through our QAP program, that is primarily the reason why a lot of labs will have a bias high or low depending on the accuracy. Because when you get much longer calibration curves, that last point at the top is going to severely influence your accuracy at the low range. And you really need to kind of know what is your target point. If 1% is your target point, you need to kind of really center your calibration curve around that 1% cutoff point. So in addition to the 11 cannabinoids, we had an interest in delta-9 THC isomers and other cannabinoids. So here's a chromatogram where it took the 11 cannabinoids in our method, and we wanted to see at the time there were an additional 9 cannabinoids that we could purchase, which included 2 delta-10 stereoisomers and exo-THC, which are highly of concern for an analysis. So if you see here highlighted in the red, or in the red box, there's a focus around delta-9 and delta-8 THC. Even though they both almost baseline results here, you can see there are common interferences from like CBNA that can be found in plant samples that eludes right in the middle of both of them. And then exo-THC eludes prior to delta-9. But you can see in part B of the figure that exo-THC and delta-9 THC have almost identical UV-vis spectra. So it's very important that you can separate those two out from each other. And I'll show you some examples of why that is a little bit later on. Now, CBNA that eludes between delta-8 and delta-9, you can see there, they have very different absorbance spectra. So you would clearly identify CBNA being present there instead of one or the other. One emphasis where we can highlight where the interferences could occur for delta-9 THC was in exercise 2 Candy QAP. The top chromatogram here was one of the samples we sent out, which is the CRM available from NRC Canada. You can clearly see where CBNA was identified in the sample and significantly co-eluded with delta-9 THC. And here is a graph showing the comparison between the participants and the COA value for that material. So for delta-9 THC is the solid green line, but you can see a lot of the participants, about 60% of them, reported mass fraction results higher than the consensus mean value, really indicating the bias high that would result from that interference. So focusing in on the other aspect of the delta-9 THC isomers of concern is centering around THCA and also delta-10. So here on the right now, you can see, looking at the two stereoisomers of delta-10 are baseline resolved, although they do interfere with some other cannabinoids present in the sample. THCA is baseline resolved, and it's not going to be an issue for any type of analysis that should be done based on the cannabinoids run here. And you can see where you get some differences in the UV-vis spectra for the interfering cannabinoids. So lastly, the LC tandem mass spec method. Here are the general parameters surrounding the method that's used. We do have a video up on our website that actually talks about the method development work that was done. Centers around using a mixture of acetonitrile and methanol with water on improving the separation, essentially focusing on 16 cannabinoids in less than 30 minutes. Here in the top right, you can see chromatograms that show, in some cases, you can see there is still some co-elution. That's the advantage of using the tandem mass spec. Allows you to be able to mass spectrally separate out co-eluting isomers from each other. This method was transferred to a forensic laboratory here in Maryland State Police, and with almost minimal changes to the method, it adopted very well in their laboratory. To validate the LC-PDA method and the extraction protocol we had, here's a publication we released in early 2022 that centered on focusing on measurements of the University of Kentucky Hemp pregnancy testing program and some hemp oils that we had. The general method that we used was 0.5 grams of cannabis plant material with 20 milliliters of methanol, vortex for 10 seconds, shake it for 30 minutes, and centrifuge it for 2 minutes. Remove the methanol extract and repeat the extraction process and combine them into one extract. This was shown to work very well in comparison to the participants who participated in the pregnancy testing program. And this was since adopted for other methods, the other analytical methods like the LC tandem mass spec and the GCMS. Then we wanted to expand beyond just those samples that we did there for plant. So we obtained some bulk materials shown there on the top left. Then also some adjudicated samples from our local crime laboratory. And then we also purchased some commercial hemp samples from the online marketplace for analysis here in our laboratory. Now, big reason that is because we wanted to start expanding from the biomass materials into more finished products. And the hemp commercial samples that we bought were really specifically towards smokable hemp products like that could be used for pre-rolled cigarettes or roll your own cigarettes. So this study, big picture wise, has been published in Police Chief Magazine. And here's a link to the NIJ website where we published a joint article with them, hitting the high points from the study. And we have a couple more publications that are in the process of coming out that go through a lot more of the detail in the studies. But first, since we had all these different types of samples, we had to come up with some type of grinding and homogenization process because we didn't have that in the initial study we did because the University of Kentucky samples came already ground and homogenized for us. So basically we purchased a portable grinder with the capabilities of being able to grind up samples from 10 grams all the way up to 50 grams. Generally speaking, the smokable hemp that we obtained ranged between 10 and 20 grams in a packet at a time. And it worked really well for this portable grinder. And basically here I'm just showing you where you tilted at an angle and you could move it backward and forth. It really helped with the mixing process, but also improving the grinding of the sample where you're constantly improving the process where you're you're ensuring the entire sample itself is being ground. Then you clean out the cup, empty it out. But then we also had to come up with a procedure for cleaning the vessels, which involve using water for a rinse, then methanol, a subsequent rinse. After you do it 4 times of methanol, you can let it air dry, and 2 hours later, it's good to go. Now, we've used these probably for about 50 to 70 samples, so we haven't had any issues by using methanol so far for cleaning. But to give you a more detailed example of it, we took a grinder chamber and we ground up a lot of hemp in it, making a really, really dirty sample. We wanted to make it much more dirty than what you would ever see for a general grindings of a sample you probably would get in your laboratory. And here on the right, I'm showing you an example of what the water cleaning looks like, and then the 4 subsequent methanol cleanings. Essentially, you remove almost all the particulate with the water, but THC, any of that that binds to the sides of the vessel are not going to come out with water. You're going to need some type of a polar solvent like methanol to be able to do that. So in this case here, you can see where the water is very dark looking. The first methanol is very dark looking as well. But as you start going through and getting more methanol washes, you really get a clear solution at the end, which is also evident shown here in this these 4 chromatograms shown for, in this case here, the chromatographic profile, UV profile obtained for this particular sample. This was a marijuana sample. You have a really high delta-9 THC peak here and THCA, and as you move on into subsequent washes, you pretty much eliminate the presence in the sample. So this is how we decided that using 4 methanol washes was appropriate. And you should do something similar in your laboratory to ensure that your process is going to be adequate for cleaning the vessel. And this should account, you can do it once, similar to what we did here, and then that should account for all of your analysis that you're doing to prevent redoing the same thing over and over again. So overall for the study, there were 53 samples in general, 34 came from one source. And what we found was that 93% of the samples, even though they were being sold as commercial hemp, they were actually found to have a total delta-9 THC concentration above the 0.3% threshold. You can see here shown on the graph with different colors, where essentially I think it was either 3 or 4 that fell below the 0.3% threshold. And here's an actual table summarizing it. And yes, there were 3 that fell underneath the 0.3% threshold, but they ranged from the 0.3% all the way up to almost 1.8%. So there's a very wide range of samples that fall within that range. Most forensic labs are looking using that 1% as their cutoff. So there's a lot of samples that do have total THC values ranging from 0.3 to 1%. Now, we investigated looking into seeing why this was. There's supposed to be a commercial hemp. And we actually looked at a lot of the websites actually included statements such as all products contain less than 0.3% delta-9 THC. Our products are lab tested to ensure that delta-9 THC content is less than 0.3%. Many of these sources even provided certificate of analysis that commonly revealed delta-9 THC levels were less than 0.3%. The problem is this is only focusing on delta-9 THC. When you take into account the THCA value, generally speaking, the certificates would actually say that it would be higher than the 0.3%. And if you actually look at the data here, now the tables are including the individual delta-9 THC value and the THCA value. If you center just on the delta-9 THC value, roughly 80% of the samples that there are in red, but those first 34 from that one source, you can see that 80% of them would be below the 0.3% just for delta-9 THC. So this really shows the importance of product manufacturers taking into account both delta-9 THC and THCA, but also for forensic labs to have a better understanding of what types of samples they could potentially see come in their laboratory. So what we also wanted to do is, and we have a manuscript following up on that Police Chief magazine article, but it really focuses on comparing NIST measurements to what was on the product label. And one of the issues was out of the 53 samples, only a small number of them, I think around 13, actually had certificate of analysis provided that matched the product label when we received it. So there was a lot of inconsistencies from the manufacturer on providing accurate results associated with the material. This could be for many reasons, but when we analyze them here, you can see the NIST results are in blue, and the product label is in black. In the case of total THC, very rarely do you see the NIST result be in commonality with the product label. And the same goes for the THCA graph in the middle and the delta-9 THC on the right. Now you'll notice that the THCA values in the middle, the NIST results were lower than the product label, but the delta-9 THC values from NIST were higher than the product label. So that's a really good indication that product storage, it was poor, and where you were seeing a lot more, in this case, you were seeing potentially degradation from storage conditions of the product where it was stored in a factory or in a dispensary potentially for long shelf life, a year or 2 years potentially. But these poor agreements not only could be a result from that, could be from poor method development work by the laboratories that send it out through. Sample inhomogeneity is a big concern, batch-to-batch variability, changes due to storage conditions, as I mentioned, but also product labels or documentations that are not representative of actual products. So essentially, they could have had it sent off to be measured when they first had it, and after it was packaged, and then 2 years later, it might not be, the documentation might not be adequate, and product manufacturers should send it off to get tested a little bit more regular. It's also a scenario where you could have a case where they get it tested when they first have it, and then they just assume that it's fine, and they don't update the documentation online like they should when they get new batches in. So this will all be discussed in more detail in the publication to come. The second manuscript that's under preparation is focusing on an overall optimized procedure for the sample preparation. In this case here, we have published and released a tutorial video on our website for processing cannabis samples that goes through from the grinding and homogenization process all the way through the end with the ready for analysis by the instrumentation. The general scheme for the extraction process involves 0.1 grams of cannabis plant, where we add 5 milliliters of methanol, vortex it for 10 seconds, shake it for 5 minutes, and centrifuge for 2 minutes. And then remove the extract and repeat it. Now I'm going to go into some detail about how we did that. So first, we already talked about the homogenization, the grinding process, but sample size. So we looked at what we got from our participants in CanQAP, and generally speaking, a lot of them range from 0.1 grams to 0.5 grams. In our original method, we used 0.5 grams, but with the idea of trying to use less solvent if possible, but also our collaborating forensic laboratories really wanted to be able to use a smaller sample size. So we ended up selecting a 0.1 gram sample size. Next, focusing on solvent extraction, we compared sonication and shaking, and we really saw no difference between the two, and ultimately chose shaking, as that would be a much more common analytical, instrumentation that they would have in our laboratory, common laboratory. Then looking at the different types of solvents, from our participants in CanQAP, we found that alcohols was used for the extraction by roughly 80% of the participants. So we centered in on that type. We focused on methanol instead of using ethanol or isopropanol because it was a cheaper in cost and should provide a similar extraction capability. Next, we looked to see how we would do with doing different extraction volume. So P represents the preliminary result from the PT study. We used the material from them, and we did the extraction using 5, 10, and 20 milliliters of solvent. And although it slightly went down as we increased the amount of volume methanol that we used, these were all within the overlapping uncertainties of the original value on the certificate. And we chose 5 milliliters moving forward to be deemed acceptable for 0.1 grams of extraction. And then lastly, we wanted to look at how long should we extract it for. If you notice here at 0 minutes, we have an extraction ranging from 88 to 92% for CBD and CBDA. This is just after we take it, add the methanol, and sonicate it for 10 seconds. So majority of the cannabinoids in the plant sample are extracted out fairly easily right off the get-go. And then you see a slight increase after you get past 15 minutes through 30 minutes for the extraction. So what we decided to do was select 5 minutes for the shaking time, But then we also wanted to do was increase we didn't want to just do one extraction, we wanted to do multiple extractions. So we looked at the extraction cycles for the process. So, and here again, you can see the spectra, or excuse me, the figure I was just showing you, where we shows the 5. The original method that we based a lot of this from did a extraction efficiency study on the number of cycles that they did the extraction. And basically what they found was that 95% of the cannabinoids were extracted in the first extraction cycle. This was using 0.5 grams and 20 milliliters of methanol. And in the second extraction, they got almost 5% and very little in the third and fourth. So we did something very similar here at NIST, and we got similar results to where the remaining 10 to 15% left over from the first extract was extracted out in the second extraction. The last part of the sample preparation procedure considers around filtering and dilutions. So measurement reasons for this are it helps improve accuracy and precision, but while it minimizes the matrix effects and potential co-illusions of small minor peaks that could be present in the sample. Instrumental reasons, it helps improve your performance while also minimizing the potential maintenance and downtime of your instrument. You really want to try and inject as many clean sample extracts as possible instead of more concentrated sample extracts. The final NIST procedure involved using a PTFE filter and then doing a 10-fold and 100-fold dilutions. This helped ensure that everything eluted were found present in our calibration curve range. So now kind of expanding it to an explosion, where I talked about earlier with the explosion of finished products, but instead of doing plant material products, we started to focus on extracts, concentration, isolates, vapes, and other types of supplements like gummies have become very popular on the cannabis industry market. So we wanted to tackle it with a similar process as we did for plant samples. So if you take that and compare with vapes and the oils, that's where we focus a lot of our work on initially, primarily because they're very simple samples to do the sample preparation for. You can see it gets a little bit more simplified because of the samples prepared, how it's prepared for analysis or prepared for sale on the marketplace. So here's just an example where some of the common ones you can find on the marketplace, not necessarily the ones that we analyze here at NIST, but generally these are homogeneous in nature when they're developed by the product manufacturers. So we don't really have to worry about that type of process in our case. The bigger question was really what type of sample size were we going to use? And in general, that's based on what are we intending to use it for at NIST and how much do we feel comfortable with using it. What we ended up choosing was 0.1 grams, and I'll show you some more about that here in a minute. But generally, the biggest thing we did run into is how to get the sample out of the container. Some of them were very simple, like what's shown here, where you just screw out the top and you easily could access the material. But there were also cases where they were fused together, where it was not so simple. So what we ended up doing was taking and you can buy at a hardware store like 20 bucks a pipe cutter, and we started to use that to basically cut the glass. And you have to do it very slowly and be very smooth in the cutting process. But we haven't had any problems with breaking it completely and doing it just as long as we took our time to cut it. And ultimately, you end up with a nice cut away that makes it easy for you to be able to scoop out the product that you're going to be analyzing. Now, this was for vape cartridges. A lot of the oils and vape liquids you get, they come easily. You can just pipette them into your extraction vial, your dissolving vial that you're doing your analysis for. Next, so we chose 0.1 grams, as I mentioned. We used 25 milliliters of methanol. We wanted to investigate how long should we shake it for. So we did a study where we took 4 different samples, took the 0.1 grams, 25 milliliters of methanol, vortexed it for 10 seconds, then shook it for 1 minute, 2 minutes, 3 minutes, 4 minutes, 5 minutes. I'm showing you the data here for some of that results. And what you saw is pretty much right away after the 10 seconds, it was pretty much evenly across the board that it had been dissolved and dispersed throughout the methanol completely. And we ended up choosing the 1 minute shaking time as the appropriate amount of shaking for the samples. Next, we wanted to look at what about the cleanup for it. Now, here's an example of what one of them looks like. These are generally fairly purely cleaned up samples that you will find on the marketplace. So generally speaking, you're not going to see a lot of precipitate in it. And dilutions really center more around the target range that you're looking for in your analysis. And just to give you an example of why those samples are fairly clean, generally speaking, plant samples are harvested, then they go through an extraction process, and then they do some type of winterization and filtering it. Then they distill it. During this distillation process, they generally convert all the acidic compounds into the neutral compounds. So you very rarely will see in commercial products THCA or CBDA. Generally speaking, it's more of the homemade products that you might see in our experience of what we've analyzed that you might see the acidic compounds in. Then the samples are packaged up. And we did something very similar to that in our first exercise of CanQAP, where the report is actually published and available to anybody through our website. We sent out 2 samples. One was more of a crude extract oil, which is shown here on the bottom right side, and then more like the finished product along with it. And what we found is the sample matrix of the oil itself really didn't have an effect on the analysis process. If labs provided results high, they were high in both samples. If they provided results low, they were low in both. So in general, that kind of wraps up with that aspect of when we wanted to do similar to what we did with plants and look at some commercial samples. I'm just showing you a few chromatograms here of 3 samples that we obtained here in our lab that we are measuring. There at the top is a very general hemp sample you'll see, where you have a fairly clean chromatogram. You'll have a delta-9 THC by itself, but we also included some delta-8 THC products in this case, because we wanted to see how would that affect the analysis that we've done. You can kind of see highlighted here in the second, third chromatogram, where you can start to see some significant co-elution occurring with the delta-9 THC peak. Keep in mind, this is probably like 10-to-1 ratio of delta-8 to delta-9. Now, if you remember earlier when I showed you nice clean chromatogram and I've got here for the standards of delta-9 and delta-8, they were almost baseline results. But here in the real sample, you can see when you have such a large concentration difference between delta-8 and delta-9 THC, you're really going to start to have an influence in your ability to measure the delta-9 THC. So even if your laboratory is not worried about the measurements of delta-8 THC, they're still going to have a significant influence potentially on your delta-9 THC measurements that you're going to make. In this case here, you would be having an example bias high potentially for your delta-9 THC analysis. Now, it's also important to point out that we did identify exo-THC in the samples. I mentioned earlier that this is like a byproduct of the process of making the oil samples or vape cartridges, vape samples. So it's not too surprising to see a little bit of exo-THC, but has very similar UV-vis spectra to delta-9, so it's important to be able to separate that from delta-9 THC. But even here, you can see there's some slight overlap in the samples. So last, I'm not going to go into detail about a lot of the work we're doing in the case of edibles, but we have done a lot of work here, and please feel free to reach out to me if you have questions. I centered around very clean samples like protein powders, or more complex foods like cookies and brownies, chocolate. And a lot bigger issue we had to figure out there was dealing with melting it and then doing something about the lipids that are present in the sample. Then we also looked at hard candies. Then also we have a lot of work going on right now focusing on chewy candies / gummies. And their types of matrix can really cause some complications for the LC or GC analysis. And I would say if you have any questions about any of these, please feel free to reach out to us, as I'm not going to have time to include it in today's presentation. But with that, I'd like to acknowledge some coworkers here at NIST. Annie Yarberry developed the LC tandem aspect method. He's also co-leader now for CanQAP. Jerome Moeller, who developed the GCMS method. Aaron Urbis, who did a lot of the sample preparation work, is still doing the work for the gummies going on currently. And we make a key point to include students in our work as much as we can. We've had 4 students in our lab and 1 postdoctoral test scientist that did work here. I'd like to thank the Special Programs Office at NIST. Then also all the work that was done presented here today was part of the 2 funded projects through National Institute of Justice. We'd like to thank them for their continued support. And then last, here's my email address. And also we have a Canvas email address here at NIST. So please feel free to reach out to us if you have any questions. And there's also the URL for our cannabis research webpage that we commonly update whenever we have new things coming out. And with that, again, I'd like to thank you for attending. And I'd also like to thank RTI for organizing and NIJ for their support in doing this presentation. And with that, have a good day, and I look forward to your questions during the Q&A. Thank you. Bye.
Hello, I'm Dr. Ruth Winokur, a principal scientist with the Center for Forensic Science Advancement and Application at RTI International. Thank you, Dr. Wilson, for providing such an informative presentation. Now we will begin the Q&A session. I saw some good questions coming in, so here we go. Question number 1. I see the substantial separation between the 9 standards in your GCMS method. With regard to case samples, namely extracts, cartridges, do you experience coelution due to varying compound concentrations? If so, how is this handled?
First, thank you for the conversation, and thank you for the Q&A, Ruth. So with the question, I kind of mentioned a little bit about it with the LC side there towards the end of the presentation, whereas you start seeing much higher concentrations, for example, delta 8 to delta 9, you start seeing complications trying to measure delta 9. Even though you do have a better separation in the GC, like with the DB35 we have, you at some point you will see similar coelution occurring where it will affect your analysis. It really comes down to what I would say a forensic lab is encountering and what they're seeing mostly in their lab to use that to kind of direct them to how they would approach it. But I would also say yeah, it's possible, especially even more as the cannabis industry is evolving, they're generating more cannabinoids, more specific type of products with more specific isomers in it. It's going to become more of an issue just using potentially a DB5. And it could be it could happen with DB35 as well. We just don't really know yet until it comes about.
Thank you. That was a good question. So the requirement specifies dry weight. We've had a lot of questions about this particular point in the Farm Bill. Is there a way to determine % moisture of the sample to standardize to the reference material?
Very good question. So the reference material we are developing will have a moisture. We've measured moisture in it. The way we did it is based on loss on drying in a desiccator for 28 days, which no forensic lab, no cannabis lab is ever going to do. I do realize that. But to get a true value, we wanted to do that so that we could, and even in that case, there's still possibilities some of the lighter terpenes or volatiles could still, over the 28 days, evaporate off. But when you put it in the oven, the results from Canon QAP Exercise 2, which that report is available, showed no oven methods have really worked that well so far, the consensus of the participants got a value of 7% when the loss on drying was 5. So really a method hasn't, to my knowledge, has been really demonstrated to be able to take care of the moisture values that are associated with that. We did look at some methods here in-house that would get the get the 5% value you would by doing it in a desiccator. But what we also found is that method wasn't necessarily transferable to other ovens. So it's not necessarily just the method you use, it's also when you try to put it in a different forensic lab on a same oven but different lab, you can see differences that could occur during that stage. So moisture is really a challenging measurement to do. And that's why a lot of forensic labs a lot of them do a decarboxylation already in the oven before they do the GC analysis to account for any moisture that would be lost during that stage.
Thank you. That was a really great answer to a point that has been brought up many times in the series. The next question, when will the cannabis certified reference material, CRM, be available for purchase?
Okay, so the NIST material, first I should say it's not going to be a CRM. It's going to be a reference material. CRMs, which are SRMs at NIST, go through a much more rigorous, I would say, uncertainty and bias evaluation. The reference material from NIST goes through a similar step, but not as detailed. And it will come with an uncertainty value associated with it for delta 9 THC, THCA, CBD, CBDA. So the main ones that cannabis or forensic labs will be looking for. But it's going to be an RM, not a CRM. That being said, it's made fit for purpose for forensic labs to review use, and it's targeted to come out this year.
Great. I'm sure everybody will be very happy to see that. Okay, so next question here is, do you foresee the necessity of a DB35 column being a point of concern for crime labs if they do not already have one set up?
Yeah, I kind of go back. I kind of answered that question earlier on in the first question, where I do think the better selective columns that you can use, you're going to get a better result moving forward. The problem is a lot of these instrumentations that are used, they're based on doing a screening for many seized drugs, not just cannabis in a lot of cases. And that's why they use a DB5, because they have a method set up in place looking for the full gamut. But you will see, I think, as time goes on, I mean, we did run like on the DB35R method, and we did have one of the stereo isomers, I think a delta 10 that co-eluted, but it was separated enough that we didn't feel the need to change. But again, as we see more isomers, more cannabinoids being focused on, it's going to complicate where you might need a better than a DB5.
Yeah, and we're seeing that on the biological side as well. As more of these isomers are becoming more prevalent, we're seeing you need to switch up your LC column. Yeah.
Well, we've had conversations about that too. And what happened is when you made your method, it was delta 9 was the only one you had to look at. Now it's delta 8, delta 10 in there as well.
So true, so true. Okay, so the next question is, could you clarify again the gold standard for testing for CBD and THC?
So that slide was kind of an overview for what is seen, what forensic labs kind of look at for what they use, which is generally an LC mass spec or a GC mass spec approach. I highlighted the significant issues with the GC aspect of it, but that has been what's considered the gold standard moving forward. I won't say LC or GC, which one's better, because you can derivatize and do GC and get accurate quantitative results. Very few in the industry are doing that, but that is an option out there. So there are methods out there where you can make both accurate measurements with both type of instrumentation.
Thank you. The next question, this is a good one. So does NIST have any monographs / reference materials available for the THC related NPSs? We seek additional references other than Cayman when verifying our standards, which can sometimes prove difficult.
Yeah, that is a very good question, because you are really reliant on the source you're getting these from. NIST doesn't have anything else available with THC in it, and we don't do monographs. The USPA, or excuse me, the USP, United States Pharmacia, they do monographs, and I know they have done work for one for THC and I think CBD. What I would point you to is if you're actually looking for like other types of materials that have THC in it, there you can, like I use University of Kentucky. They do have their PT samples available afterwards. They're not a full-blown ref. They're what's called a quality reference material. But they basically take these results from their PT study and assign a value afterwards. But hopefully by the end of this year, there will be by the end of this year something that you can use from this. And I would say is we're not stopping just with the plant. We are looking beyond there and seeing what else we could potentially do.
Great. I'm sure lots of people will be very happy about that. Okay. Okay. So this is a good one here. Could you please repeat the concept of not using too many points in your calibration curve and the notion that higher concentration points could skew the curve? How do you determine the optimal concentration target range for your curve?
So in our case, since we knew we wanted to do sample dilutions, we knew we wanted to target at the very low end what you might see in a sample. What a lot of people don't realize is as you build, like our curve is generally around 1 order of magnitude, but as you build orders of magnitude out from that calibration curve, the curve is going to be dictated by the tallest point in your calibration range. So if you have 3 or 4 orders, if you actually zoom in, I didn't include it in my presentation, but if you actually zoom in at the bottom portion where you would see 0.3% a lot of times in your sample, like when we did 0.5 gram or 0.1 grams, you're going to see the line does not fit your curve very well at all. And it's one of the issues we've seen in Canon QAP with THC, with making the measurements, or in plus with like CBD, as you get higher concentrations of the cannabinoid, you really start to get various where your bias either low or high, depending on if you're using a wider calibration range or a more targeted approach. I usually tell people if you're doing a 1% decision point in your lab, that's where you need to be the most accurate at. So you should kind of target, do the math based on how much sample you have, how much volume you're using for the extraction, see where that 1% is going to be at in your calibration range, and really try and make your calibrants around that point. So it's very similar to what they're doing when they do a single point assay, trying to make a decision point that way. Just this case, you're doing it more with like 3 or 4 calibration points instead of 1.
And would you recommend that labs plot their residuals off the curve?
It really depends on the person. I mean, it does help, but
it does show you how much that top point is
right. It does show you how much
biasing your curve. Yeah.
But a lot of times it depends on also the experience level of the analyst doing it as well, and what the amount of time and effort they have that they can put into it. But residuals do help you see the variations that you're going to see there.
Great. The next question is about LC-MS. Is there any matrix effect seen in the detection process using LC-MS? So
fortunately, we haven't really seen anything that much when we do LC tandem spec. One of the reasons why there is because you're getting into a very selective detection method, as you know from your biological side. What I would say also is even with the LC tandem spec, with it having the improved sensitivity, we still did I think a 50 times dilution, 1 to 50 dilution. So a lot of your matrix effects, when you do a dilution, you're able to remove a lot of the effects that you might see if you ran a non-diluted sample.
So this is an interesting question about what you would do if the concentration, I'm assuming this means in the sample, is below the limit of detection.
All right. So that depends on how your laboratory would be reporting it. I mean, in our case, like in Canon QAP, we usually tell laboratories to report based on if it's below their limits of quantitation. Because limit detection is based on if you see it. Limit quantitation is based on the lowest limit that you can quantitate. And that's usually how we tell labs in CAN and QAP to report their results. But that also varies. Some labs will have good limits of quantitation, some labs will not. So it really varies. That's one of the things we've noticed. Some labs have it really close to that 0.3% threshold, and some labs will claim 0.003 or something like that.
And the next question is about internal standards. So what would be used as an internal standard when estimating? I'm assuming they mean estimating percent.
So originally, when a lot of this started a couple of years ago, there was a steroid. The name's eluding me, that a lot of labs have looked into starting to use. But from my interaction with a lot of forensic labs, it seems a lot of them have kind of shifted to the labeled THC value. One of the reasons why a lot of labs were hesitant to do it was because it would co-elude with THC in the chromatogram from the sample, and you wanted to make that distinction easily, make it more easier, make the distinction between that and the internal standard. But some labs have told me they have been able to actually implement Delta 9 D9 label instead of D3, and it's actually you're able to get some separation between them to where you can make that identification purposes. So I would always encourage labs to use isotopically labeled internal standards as much as possible.
Yeah, those higher deuterated labeled ones are really great for getting separation. They're more expensive though. Okay, and I think this will be our last question. So this one's a little bit off topic. I'm not sure what we're going to be able to do about this one, but from the analytical method, but it was slightly off topic from the analytical method, but does NIST have a stance on the legality of THC isomers other than Delta 9 THC?
So I saw that question. That's why I started agreeing. NIST is a non-regulatory agency. So we don't actually have a stance on any aspect of the legality about Delta 9 THC or THCA or Delta 8. We try and develop analytical tools for the forensic laboratories that where they have a stance they have to make based on what the regulation is. But it really doesn't factor in. We don't have any decision point on any of that. So it doesn't really influence the work that we don't try and stipulate out any of that in our research. We focus on the science aspect of
it. Right. Okay. So we are out of questions and out of time. So so there's no further questions. We're going to go ahead and wrap up today's webinar. Feel free to contact our presenter if you have any further questions. Thank you so much for attending, and thank you, Dr. Wilson, for being here with us today.
Thank you to you and everybody else too.
Before you leave today's webinar, I'd like to draw your attention to our feedback form. It takes less than 5 minutes to complete and can be accessed via the checkbox icon directly above the chat. Your honest feedback is invaluable as we continually search for ways to improve and provide the best experience possible. Lastly, across the top of the live stream window are links to our social media profiles, including Twitter, LinkedIn, and Facebook. There is also a link to the FTCOE website, the Just Science podcast, and the FTCOE newsletter registration. Like, follow, or subscribe to stay up to date with everything the FTCOE is doing in support of the forensic community. Thank you again for attending, and we hope everyone has a great day.